Okay, what's the window size? What's the definition of a window size in a sliding window protocol? What's the window size? Anybody else can give me a... Yeah, it's the maximum number of unacknowledged frames that the sender can send. Right. And what's the maximum sequence number we can use in sliding window protocol?
It's 8 or 128.
The modulo decides, right? Yeah, it's the modulo minus 1, right? Usually, if modulo 8, you never get number 8. You get to 7 and then recycle before you get to 8. Okay. And who would discover a data frame, a lost data frame? Who would discover it, the sender or the receiver? Yeah. Yeah? The sender. Okay. The answer, but not the right answer. Receiver. How would the receiver discover it?
That sends acknowledge of.
How does it discover? How does it know there's a frame lost?
The sequence is not appropriate. Sequence is not correct.
Sequence number, or what do we call the problem? That allows this receiver, or what would the receiver call this lost frame? It's an out of sequence frame. It will discard or decide this is the wrong frame based on the sequence number. Which one is better, the go back in or the selective reject or selective repeat protocol? Which one is better? Which one is worse? The go back is better or worse? Worse? Good answer, but it's not the right answer. Which one do you think is better? Selective repeat is a good one. That's the wrong one. Now, compare the two.
Go back in, the disadvantage of selective.
Say with the okay. So the go back in has a disadvantage, and that's Kamus, and that's using the channel inefficiently. It's inefficient at using the channel. Transmit good frames, it will transmit them again. And what's wrong with the selective reject? Selective reject does not retransmit frames again, good frames. So what's wrong with the selective reject?
You need more memory.
More memory is needed. How much memory is needed in the selective reject?
1 minus Windows X.
Answer? How much memory is needed in the selective reject? Huh? So, how much memory does it need? Detail. Less than one more than the window size. How much memory does the selective reject need? Pardon? Okay, do you want to try? Okay.
The worst scenario is the size plus one, but it depends on the.
How much windows needed by the selective reject? Guys, yo! How much memory does it need? Sorry. Okay. And how much memory is it does it need?
What's the scenario?
Thank you.
Window size minus one and set.
Sender and the receiver. Everybody's answering me about the receiver. I didn't ask about the receiver. I said how much memory is needed by the selective reject. You should say the sender needs so much and the receiver needs so much. What about the go back in? How much memory is needed by the go back in protocol? Yeah? Pardon? To go back in. Only the sender needs memory. How much memory does the sender need? Pardon? Equal to the window size. Equal to the window size. As much as the window. As much memory as it will take frames to. It needs memory to hold frames that are equal to the number window size. Okay. Why would a machine request a link setup or reset? What condition would make one of the users say, let's reset the link?
Error can be solved by transmission.
If we get errors, they cannot be solved by retransmission. Such as, anybody give me an example?
Well, it's a number.
Thank you, Cici. I have somebody else here. I want to close them. Okay, for example, our window size is 5, I sent you 5 frames, so instead of sending me acknowledgement 6, you send me acknowledgement 4. Would that necessitate a reset?
No.
Okay, give me then a better example.
If the acknowledgement is
Outside a certain range, the expected range, okay. So if I send you frames 1 to 5 and you send me acknowledgement 80, that's way out of place. And that would require, by whoever receives this, the sender in this case, reset the link. Okay, what are the steps involved in resetting the link? There are about 5 or 6 things to be done. Name one. But in an exam, you'll probably have to name them all. Go on, give me one thing. What happens in a link reset? All previous communication calls are terminated. Yeah, anything else?
The link is off.
Pardon?
The link is off.
Notify the user that the link is gone. Yeah, anything else? Clear all memory of all frames. Anything else? Zeroize all counters. Always zeroize the counter, so even for resetting, we'll zeroize all counters. Anything else left? Probably there's nothing left, right? Okay, no, but there's always one or two things always left. Okay, anybody else knows what's needed up there? Yeah? What do we call it? The receiver ready frame is exchanged. So both sides must send a receiver ready. That's the last thing in the resetting the link.
Packet that was sent has some error. So,
It may not be necessarily the first.
yeah, the packet with sequence 0 has some error.
Yeah. Packet number 0 may have an error. What else could acknowledgement 0 mean?
Not send any packets. Haven't sent any packets.
I've sent you, oh, if I send you a few packets, you send me acknowledgement 0. What does it mean? Sent you any packets yet? I don't think that's the reason it's used. It has another meaning close to that, but anybody want to give me another meaning of acknowledgement 0 other than what was that reason he gave me? Who was it? Was it you?
All the packets before 0 are fine, and
Okay,
you have
thank
to
you.
send.
Okay, so all frames before number 0 are okay, acknowledged, and that's the next frame I expect to receive from you is frame number 0. What else can it mean?
0 is lost.
It could be frame number 0 is lost. It could be frame number 0 has an error. Anything else? After resetting the link, setting up the link or resetting it, we exchange a receiver ready frame, which is an acknowledgement 0. And what just it was, we sent few frames and I got acknowledgement 0. We're not resetting the link, we're not in the middle, we're not starting communication. We're in half the day through continuous communication. What frames are acknowledged if I send you acknowledgement 0? Acknowledgement 0, I mean, I have not received 0, but what have I received? Yeah, what's before 0? What frame is before 0? That's acknowledged. And if I send you acknowledgement 0, I'm acknowledging some frames. What frame number is acknowledged if I send you acknowledgement 0? Pardon? It depends on the modulo. It's modulo -1. If it's modulo 8, then I've received number 7. If the modulo is 128, then I have received, it's an acknowledgement of 127, and so on. If it's modulo 512, then it means I received 511, 5,011. Okay. But just one more thing I want to mention about this, and then we get moving to a new topic. Something called a piggyback acknowledgement. There's an acknowledgement known as piggyback. Okay, anytime we talked about communication between two neighboring machines, I always mention it's the sender and the receiver. Are we okay on this? No? The sender and the receiver. Sender and receiver can maybe, there might be few machines connected to a router, and there could be a number of routers. Some routers are kind of connected normally to one another in some kind of a network. And usually every network should have maybe at least two routers, maybe. Most of, yeah? This is a switch, for example, a local network. It might have two routers connected. So every device on this network and every router on the same network, they are direct neighbors. And that's what we've been talking about. The data link layer is the communication between these two machines, or those two machines, or machines in any other local network. But sometimes you want to bring the communication to another device. That device want to communicate to that device. So this has to be sent to a router. So these are neighbors on this router. But that router also has another link to another switch or another network. And these two routers here are neighbors. So we might want to send the information all the way to this router. And then eventually it will be given to this device, passed on to this device. But the point is that, trying to look at here, is that there are lots of routers that information will normally go from one router to the next. And routers in this case are like neighbors, that they're talking at a data link layer level. So they're passing the packet in a frame, and the frame is delivered to the next router and the frame, or the packet keeps going from one router to the next inside a frame. Now, so when this router is sending information to this one, we call this the sender and that's the receiver. But also don't forget that there could be information flowing in the opposite direction. So from this device, it's to be sent to that device. So it goes from this device here through to the router or to the switch. I should have connected those here. Sorry. Another switch. So it's just all the links that are available in networks that this device now want to send a message to this device here. It will send it to the router, which is its neighbor. But this guy puts it into a frame and passes it to this router, who puts it into another frame and passes it to this router. Eventually, it will get to final delivery. So the point is, while we're sending information in this direction, this router also could be sending information in the opposite direction on the same lines. So while this one is a sender and that's a receiver, and they have a sliding window on their own, and modular number, this router is also a sender, and this one is a receiver. in the opposite direction, and they have their own separate sliding window and separate modular number. Probably the same modular number, maybe the same window size, but they're completely different. Like management, like if this one is sending, for example, let's say they both use modulo 128, and they're using sliding window 5. Just coincidentally, they both, in this direction, they could be using 5 in this direction, and this direction could be 12, the window size. So the point is that the two traffic of information going in opposite direction are independent. So when this one, for example, is sending frames 0, 1, 2, 3 in this direction, 4, just to make it sliding window 5, this is probably sending frame number 75, 76, 77, 78, and 79, or 74, starts at 74, there you are. So it's sending in this direction, they're reaching on their own window, separate window altogether. So in two different directions, there's traffic flowing. And there may be more traffic going in one direction than the other. There could be both heavy traffic. They're absolutely independent, but they're using the same links, the same wires, because maybe it's full duplex. And what's a full duplex link? Do you know what a full duplex link is? What's a full duplex link?
Send and receive and both.
You can send and you can receive on the link
Same time.
at the same time. Don't forget, it's simultaneously, yeah. All right. So why am I telling you all this? Because if this guy is sending information in this direction, 0, 1, 2, 3, 4, it's expecting an acknowledgement. It's waiting. The sending part of this machine is waiting on an acknowledgement. And also here, the sender is separate and has its own memory, and the receiver has its own memory, and in the opposite direction. So, but anyway, it's waiting or expecting an acknowledgement to be sent in the opposite direction. Let's say acknowledgement 5. But they say there's a lot of traffic going in that direction. Why should we send another packet number 5? So what they've decided to do, every frame that's sent in either direction, if this is the frame, this is the user data, but every frame has a header in the front. What kind of information do we put in the header? Anybody knows? MAC addresses, source address and destination address. The address of this machine and the address of that machine that's sending it on this local network. The address, MAC address is only used locally, even though it's unique. But so we're sending source address, destination address, sequence number. Anything else? What they decided to have another field here, spare field, nothing to do with this packet. And they said, if you want to put anything in there, we'll carry it to the other end. So what they decided to do, this acknowledgement that needs to go in this direction, this sender, instead of sending a packet, an acknowledgement packet, it looks, do I have any traffic going that direction? It's like you have a friend of yours, and you know some friends are going to Cork tomorrow, so you say, and your friend wants to go, so you say, oh, come with me, go and see if any of them is driving today. And if they're driving, do they have a free seat? And you put your friend, get him a free seat on a car that's going in that direction. So if there are frames going in this direction, so this guy, instead of sending acknowledgement 5, it will put the 5 here on the header of those packets going in this direction. So that's, instead of sending a full acknowledgement frame, it looks, is there any information frame going in that direction? Yeah, we'll put this number on it. This number has got nothing to do with this packet at all whatsoever. And as soon as this packet gets there, the sender part of this is, remember, there is a receiver here. but the sender will come and take this number of any packet that comes in. It's given to the sender, and that's an acknowledgement. So it saves the system sending separate acknowledgement frames. But if this guy receives those frames 0, 1, 2, 3, 4, and wants to send an acknowledgement, comes down and look at the sender side and there's no traffic going, well then it has to create an acknowledgement and send it back in a separate acknowledgement frame. So this is only used if there is traffic going in the opposite direction, and most of the time there is traffic going in the opposite direction. So this is called a piggyback acknowledgement, because piggyback is a term used to get a free ride. Here they pick the child, a baby, put him on your shoulder, you give him a free ride. They call it piggyback. So piggyback is getting a free delivery or a free ride to another location. And that's how it's done on this one. This is like you wanna travel to a city this weekend, to Galway. You go at the motorway, at the start of the motorway, and you stop at there and thumb for a lift, or maybe hold a piece of paper called Galway. So cars are going there anyway, which is just like the frames. But if there's a car with free seat that they decide to stop for you, they stop, you get in, you don't know nobody in the car, you're delivered, you're dropped in Galway, and that's it. So there's no relationship between, this number that gets delivered and the packet it's in. So that's known as piggyback acknowledgement. Okay. So the next thing, one final point, and it's called framing. Framing is also a responsibility of the data link layer. So did we do error detection? Yeah, we went over error detection, and we've done flow control. These are all responsibilities of the data link layer. Framing, building a frame and identifying a frame and using frame, this is a specialty of the data link layer. So anytime the data link layer wants to send information, it's given information. Normally it's given a packet. Decide out of its own, I'm going to send some information. Data link layers don't send information, or very little for management purpose, but usually a user wants to send data. It's put in a big segment up at layer 4, and then at layer 3, that's the packets layer, the network layer. It breaks it into datagrams and give them numbers, sequence numbers and all that, and give them to the data link layer, say, can you please deliver it to that router or that router? That's what the network layer does, decides which route it will go. Link layer, it takes that packet, but it does not send a packet. It has to put it into a frame. It might put 2 frames, it might take a packet and a half, put them in a frame, but it does not send data as it is. It has to put it into its own unit, which is called the frame. So it builds a frame either around it, or builds a frame and put the data in it as much as it can take, and sends it wherever it was told. The data link layer does not decide where to send. The data link layer might have 2 or 3 links. It's the higher layer, network layer, that say put it in link number 0, or link number 1, or link number 2. Routing is done at the network layer. Data link layer is just responsible for delivering the data to the required neighbor. And if there's something wrong, it will detect it and might retransmit it. So building a frame is an important for many different reasons. Because first, this is the unit it will understand. And if there are a number of frames involved, they need to be sequence numbered. So every frame will have a header. And also every frame has something called a trailer or a footer at the end of the frame. So information is added, yeah? So the information is added to the frame at the front of the frame and the back of the frame as well. The front of the frame, we call it the header. Usually the frame is a packet, usually. Most of the time. It could be more than a packet, could be less than a packet, but a frame is built to carry the user, the data that we receive from the higher layer. For now, we just say user information. We don't have to call it packet. It doesn't know it's a packet. It doesn't know what's inside. It knows our 500 bytes to this neighbor, and that's all it does. So if it's the sender, it will build the frame, and it will, for example, a number of bytes at the header of the frame. It needs to tell the other side, what kind of frame is this? Is this a frame that's carrying packets, or is it an acknowledgement frame? Or is it a reset frame? So, so in order for the receiver to know, what am I getting from that end? Oh, this is information packet. Then there's a type, a frame type that identifies this is an information packet, or this is an acknowledgement packet, or this is a link reset packet, or a refusal packet, or a disconnect packet. Disconnect, that means that's it. I don't want to communicate with you anymore. We're closing down today. And also, if you receive a disconnect packet from your neighbor, you can say, no, I want to continue. Reset or disconnect, you cannot continue. But so there is a frame type. There's a control frame, a control field. It will probably be the sequence number. Okay. We'll need to, like if you need to program it, you need to look actually at the protocol you're writing. Which bits in the header represent the frame number, the sequence number, and which bits also the acknowledgement number. So normally every frame also carries a sequence number and an acknowledgement number in the opposite direction, and also each frame will carry the addresses, MAC address, source and destination. So the header can be reasonably big. Anybody knows what goes in the trailer of a frame? What information is put in there? Most likely, if CRC is used, that starts checking the information here. Remember, cyclic redundancy check. Remember that part is storing a bit at a time. And by the time we reach here, we can start transmitting because we don't need the start bit. Remember the part that we divide the long division or the XORing, and we keep the remainder all the time. And by the time we finish all the end, we have a remainder. We leave it here in that field. So this field here is called CRC. Finally, every frame in most, protocols uses something called a flag. A flag. A flag is a signal, special sequence that indicates the start of a frame and the end of a frame. One of the fields here is also frame size. How many bytes does this are we carrying? How many bytes is the size of the frame or the data, depending on some protocols? But that's the first error that normally they check as well. If the user is sending you 200 bytes or 2,000 bytes, and you keep going, you start at the flag and say, okay, I'm counting the bytes until you find the next flag, and you find 2002. There's discrepancy. So if somebody tells you I'm sending you 2,000 bytes, and you find 1,900, that means something is wrong with the frame and it's discarded. It's one of the errors in frames usually, frame size. And so this is the general idea. So how did they came up, or how did they eventually come up with this? In the older days, the first form of communication between neighbors was in a mainframe. You've heard of mainframes? Computers. And a mainframe used to have one big CPU and memory, big memory as well, and maybe 100 devices that are all connected to the mainframe. It's probably the first idea of a local network, but at that time they've done it because technology wasn't there. We only had one CPU. When they started first, they used to call these dumb terminals. That means they have no CPU. They're only screen and a keyboard. That's all they have, a screen and a keyboard. Later on, they became a bit more sophisticated. They had their own CPU, and then they became workstations, they called them, and then we started having our local networks. But that's the first kind of computer, first form of communication. How did they? Now, it's communication, and anytime this guy wants to execute a code, a command, or run a program, like just give me the list of my files, dir or whatever the operating system lists the file names. It has to write the command, hit enter, that command is sent out there, it joins in a queue list of commands received, and then the CPU, the operating system, will take it, read it, and find the results, and gets the result that needs to be displayed on the screen, sent out to this guy here, and it's displayed on the screen. And that's every command you did. That's the way it worked. Now you have your own laptop. You type the command, goes to your own CPU, and the result is displayed on your screen. But in those days, they didn't have a CPU on the device. They had to send it up to the central machine. That's where the CPU is. So at the time, they used to get lots of commands. So they needed to differentiate between the commands. I'm just bringing you the general idea so you know how frames are identified now. So they agreed anybody can send a command. Commands have different lengths. There's some commands that are 3 characters, like dir or list. Give me the list of files. You send it, you get it back. But then you might want to have a list of files that start with the letter B and any length. So the command can be of variable size. And so when commands are sent, some commands are very short, some commands are very long. So this guy here, when they're all written in memory, one command after the other, it needs to, where's the end of the command? To pick one command and go and deal with it. And then the next command is short, and then the next command is really long. So they needed to identify command separator. And they agreed. They said, okay, then let's get any character that's not used. Let's say hash. So they put hash at the start and the end of every command, or the start of every command. So all commands are separated by hash character. And then, so now the operating system keeps reading until the next hash, and then executes it, then go to get the next command, and so on. But then they started becoming sophisticated. They said, okay, now I want you to print something for me, a string on the screen, and one of the things I want to print is a hash. So it's part of my data going there. There's hash in the middle of it. So when that joined there, there's a hash there, but that's not really the end. Here's the end of the command. But there's another hash here. It's part of the user data. So that caused a problem. They said, okay, no, we can't use that. Well, they found a simple solution for it. They said, okay, don't use this special character, whatever it is. Don't use hash. But if it's part of your data, well, then put double hash. So we use this protocol. If we find 2 hashes, that means they are not end of command. That means get rid of one, and we'll treat the second one as part of your kind of user data. And then the idea got worse, and then say, okay, what if I want to send 2 hashes? Well, then put a hash in front of each one of them, so you end up sending 4 hashes. That wasn't really a perfect solution. And then they said, no, use some command for start of your message and some command to some special character to indicate the end. So eventually, they said, no, they came up, one of the protocols came up with this idea. I think it's called the HDLC frame. It's one of the most famous, one of the most used protocols for data link communication. They're using a frame called HDLC. It's High Data Link Control Frame. But anyway, the idea, and they said, let's use a flag. Let's have a special sequence called a flag that indicates the start and the end of the frame. And the flag is it's 0, 1, 1, 1, and a 0. So that's the flag. It's 1 byte that has this special sequence: 0, 3 ones, and a 0. And also at the end, so every frame must be kind of between 2 flags. So whenever you create a frame, you create the flag, then followed by the header of the frame, which contains not user data. And then if it's an information frame, then it'll have user data. Acknowledgement frames don't have user data. The link reset does not have user data. It has its own information, but usually the rest of them don't contain. So it's the largest is the user information frame that contains user data. And largest because of this field, this big field, that if it doesn't have it, then it's okay, we don't need it. And then we have the CRC, or they call it the frame check sequence, or CRC. Finally, you must have another flag. It's another 0, 6 ones, and a 0. So how does that work? And what happens if inside this information, remember everything goes out in binary. What happens if we get a similar sequence to this one? Which is possible, quite possible. That's not a unique kind, not very unique. So imagine if there was the information that's in there is something like this. And there it is. Now we want to add the flag, 0, 6 ones, and a 0. And then the next frame starts after that. A flag can indicate the end of one frame and the start of the next frame. So now we have this frame, or this flag, indicating the start, and there's more information there. So the previous frame. So, and when the physical layer receives it, just puts the information in memory. Doesn't know what it is, the physical layer. Like the data link layer of the other machine would create a frame, put a flag at either end, and say transmit all this, including the flag. So the frame is received at the other end by the physical layer. Physical layer puts it in memory and calls the data link, say, yeah, there's more data for you. So now the data link layer comes in and looks at memory and start going searching through memory. It cannot deal with the data unless it identifies a frame. Because once you identify a frame, you know what's in the first byte, what's in the second byte, where's the information frame, you know what kind of frame it is, you know what sequence number, you need to know where is the start of that frame. So in order to find out where the start of that frame is, you search until you find a flag. You find a flag, that's it. Now you know. That's indicating the start of my frame. Now that's the first byte of my frame. Whatever information is there, now I can dig it bit by bit if I want. I can look, I know which one is the sequence number, which one is the frame type, which one is the frame size. All information is reasonably clear from there on. But it's so important to find this. And once it tells you the size of the frame, then you also need to go all the way to the end to find out where this CRC is. And in order to know what CRC is, because CRC can be any bits as well, there's nothing unique about them. And then you have to find out where the next flag is. So you go and look for the first flag, keep looking until the second flag. Once you find the first flag and the next flag, say, right, good. Everything between those is my frame. Now you can start dealing with it. I know maybe the last 2 bytes, maybe they're the CRC. Then you know that's not part of our data. And you know where the header is. So you can pick everything. You can deal with the frame once you know where it starts and where it ends. And you know the agreed structure or protocol with the other side. How many bytes are there in the header, how many bytes are in the trailer, and so on. So this is the general idea. Now, the problem is, here it is, this guy starts looking at the flag, looking for 0 with 6 ones and a 0, and then it wants to find the end of the frame. So it's looking for the same sequence again. But as it's looking, it keeps checking here. Is there a 0 followed by 6 ones, a 0 followed by 6 1? Oh, here's a 0 followed by 6 ones. And could say, hey, this is the end of the frame, when it's not. This protocol puts another step. The sender, when they send their frame, when they create the frame, and they put a flag before it and after it, they must make sure there is no sequence inside that frame that looks like a flag, that the receiver may mistake for a flag. So they thought of another step, and it's called bit stuffing. An operation that must be done by the sender. And what bit stuffing is, it says, look for this. If you find something that looks like a flag, insert a 0 between the ones to make sure it's not a flag. It doesn't look like a flag. So how is it done? You start counting. Remember, the flag is if you find continuous 6 ones followed by a 0, like 1 0 on one end, 6 ones and a 0. That's what the flag looks like. A 0 followed by 6 ones and a 0. So they said, okay, let's make sure there are no 6 continuous ones that follow the 0. Doesn't matter. So as the information is being transmitted, this guy looks and says, okay, that's a 0, 1, 2, 3, 4, 5. No, this is a flag. So we allow that. Let's say this one, we start at this point, 1, 2. That's a 0, there's 0, 1, 2, 3. Oh, okay, that, followed by 0. That's not a flag. So it actually checks how many ones are there. If it finds 5 ones, it doesn't even wait. Maybe the next one is a 1. No, we don't want to wait. Insert a 0. So in fact, bit stuffing is insert. What does the sender do? Insert a 0 after 5 consecutive ones. So if you have 5 ones consecutive, that means one immediately after the other, nothing between them. So if you get 5 consecutive ones, we'll insert a 0. So in this case, as it gets to this point, so it's looking for 5 ones. 1, 2, 3, followed by 0. Start counting again. 1, 2, 0. Start again. 1, 0. Start again. 1, 2, 3, 4, 5. Hold on. Let me put a 0 there. And that's where this guy here will, 2, 4, 5, it will insert a 0 here. So this 0 is not really part of the user data. It was inserted by the sender for one purpose, well, for the function of called bit stuffing. Bit stuffing, ING. So bit stuffing is inserting a 0 after 5 consecutive ones. So there might be few 5 consecutive ones in a frame. Either 5 or 6 or 16. So every 5, it will insert a 0. Every 5 ones, it will insert a 0. If it finds 100 ones, there'll be a few zeros inserted. 1 0 after every 5 consecutive ones. So this is called bit stuffing. So now When the receiver receives, only the main flags remain. They're not interfered with. So the sender makes sure all the data inside the frame, there's no 6 ones and a 0. And then, but it only sends the flag at the start and flag at the end. Or, you know, a flag can be indicating the end of one frame, next frame. So now, when the receiver comes to check, it checks this one, finds a flag, great. Says, I need another, where is the next flag? So it will never find a flag because there are no 6 ones allowed to be there. And if it finds those 6 ones, then it will stop and say, okay, that's the flag. Of course, there could be an error and you get there, but let's say one bit here changed. This 0 during transmission changed to 1. Then this guy will say, okay, there's a flag, but hold on, in my header it says there should be 4,000 bytes, there's only 2,000 bytes. I'm gonna discard this frame. It discards it. So that's the idea. Now, but of course, we are after modifying, changing the data. Remember, somebody gives you some stuff to deliver. Don't change it. But if you change it, you make sure at the other end, we put it back the way it was. So now, at the receiver at the other end, must do an opposite operation to bit stuffing. And it's called bit stripping. That's removing the extra bits that were inserted by the sender to hide the flag. So bit stripping will go, apart from the 2 frames, it'll go right through. If it finds any 5 ones with a 0 in front of them, it will remove that 0. So it'll find this and it'll remove it. Now, data goes back to the way it was. Bit stripping is deleting or removing any 0, of course, after 5 consecutive ones. And what's the purpose of bit stuffing and bit stripping? Bit stuffing is to hide, to make sure the user data or the frame does not contain a sequence that looks like the frame flag. And bit stuffing is, or bit stripping is bringing back the data. If there's any change done by the sender, it will be undone by the receiver to the data. Because remember, somebody gives us like a number to deliver, you don't want to change that number. You might change it during transmission, but you need to put it back. And that's how it's put back. All right, so, yeah.
So when they're doing this bit removal, what happens if the sender sends 1, 1, 1, 1, 1, 0, right?
After 5 ones, there'll be another 0. So there'll be 2 zeros. And for example, here's the data, user data, is 1, 2, 3, 4, 5, right? That's all. Apart from the flag at this end, flag at this end. The sender, well, let's put a few zeros and 3 zeros. So now the sender, when it gets to this point, 1, 2, 3, 4, 5, it doesn't go to that one and count. Is that a 6? Maybe I should go back and stick a 0. No, if you find 5 consecutive ones, put in a 0 there immediately after the 1. Even if there is a 0 in front of it. Like some people might say, okay, 1, 2, 3, 4, 5, 0, 0, 0, 1. What do we do here? Yeah, you go count. If you find 1, 2, 3, 4, 5, you must put a 0. Now, look at the receiver now. The receiver comes in, counts 1, 2, 3, 4, 5. Here's a 0, remove it. I know it's not a data, it's something that was added by the sender. 1, 2, 3, 4, 5, there's another 0, remove it. If you are sending data, say 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Now, this example here, if this is the data, will the sender do bit stuffing at this stage? It will count. Zero zeros. Every time there's zero, restart the count. So here's the restart the count. 1, 2, 3, 4, and a zero. Nothing here. There's no 5. 0, 0. We start here. 1, 2, 3, 4, 5. Put a 0 in there. So here's a 0. We added a 0. There's also already a 0. Keeps going. 1, 2, 3, 4, 5. Add a 0. And another example. And the receiver will do the same thing. We'll count. Is there 5 ones? 1, 2, 3, 4. No, there's no. 1, 2, 3, 4, 5. Yeah, well then get rid of this 0. 1, 2, 3, 4, 5. Get rid of this 0. Another possibility. Imagine this. 1, 2, 3, 4, 5, 6, 7. What would the sender do here? Where would the sender insert the zeros? It'll count. Let's imagine just there is a 0 here, so we're okay. So it counts. 1, 2, 3, 4, 5. What's a 0? 1, 2, 3, 4, 5. Another 0. 1, 2, 3, 4, 5. Another 0. 1, 2, 3. That's it. The receiver will do the same thing. Start counting. After every 5, it will remove the 0. 1, 2, 3, 4, 5. Remove this 0. 1, 2, 3, 4, 5. Remove this 0. So if this step, the 2 steps are followed correctly, we will have no change of the data. The final data received is exactly the same as the initial data sent. But also, we will not have sequence that looks like a frame. Yeah?
Why we cannot add a 1 instead to make that 5?
Why would I add 1? This is the user data.
If there are,
Remember, if this was the frame, there'd be another flag here. 1, 2, 3, 4, 5, 6, 0. And there'd be a flag here. 1, 2, 3, 4, 5, 6, 0. So these are the flags. That's the frame. Why would you add 1? You will make you. Yeah, well, I don't know if adding a 1 would do, but that's the protocol they agreed on. That's the agreed protocol. If you need to add 1, well then do you add 1 here between these 2 zeros? Then you have to add 6 ones. Or only if they were has 4 ones. If it had an extra 1, then the sender would insert a 0 in front of it. If it's 4, leave it. We don't want to change the user data. We want to minimize the change. Okay, let's see if we have anything on the slides for that. Okay, so some of the functionalities of the data link layer are the framing, error control, flow control, and link management. Link management is kind of between data link and physical kind of operation. But let's just stick now to those. So let's look at framing briefly. First, you need to know that there is a connection and connectionless. There is an acknowledged and unacknowledged communication. We talked about those when we did the switching and the datagram switching technique and the virtual circuit switching technique. The connection or connectionless, the connection communication is where a link needs to be established We're not talking about physical link, but kind of the receiver should know about the communication. So a request is normally sent first, like telephone calls, they are connection oriented. That means even though you have physical link to the receiver, but you cannot talk to them unless you initiate a link setup or a connection with them. So they call this connection oriented. Connectionless is the example of the datagram, where you don't have to tell the receiver you're going to send them data. The receiver does not know you're going to send the data, or you just put all the data together and forward it, and it will be delivered there to the receiver. That's called connectionless. What about unacknowledged? That means you will not hear back of the data you sent, whether it's been delivered or was not delivered. Being delivered or not delivered is an acknowledgement. Even if it's not delivered and you're told your data is not delivered, that's good. That's acknowledgement. At least you know it was not delivered. But the unacknowledged service is the one that you're never told. You don't know whether it's delivered or not delivered. So services can be unacknowledged, connectionless. That's almost the data, the IP operation, the internet protocol. It's connectionless and it's unacknowledged. That means you don't have to connect with the receiver, and when you send data, you don't know whether it's delivered or not. And then there are services that are acknowledged and connection. The opposite side is the acknowledged and connection oriented. That means before you send the data, you must get linked to the receiver, send the data, and you'll be told whether your data is delivered or not. So that's acknowledged and connection oriented. And there is acknowledged connectionless as well. So there's a kind of number of services. So a lot of the networks now are providing a lot of the services. Even at the internet level, they get into the TCP/IP communication at level 4. Part of it does not provide any connection or acknowledgement, and the other part provides some sort of connection and acknowledgement. So the main task of the data link layer is to provide service layer above it, which is the network layer. So the main task of a data link layer is to serve always, every layer serves the layer above it. So in this case, the one above it is the network layer. But we don't necessarily need to specify it. Just say it will serve the higher layers, usually a user. To the data link layer, the user is the network layer. And the network layer has another user above it, level 4. And then level 4 has the actual users. The service involves providing facility for sending and receiving network layer units, data units. Now packets, it's a frame, but the network layer will give us a packet and we'll deliver it into a different unit, a frame. So the main task is to accept a packet from the network layer, accepting row bits from the physical layer. So the data link layer is between the network layer at the top and the physical layer at the bottom. At the top, we get bits, but they're in a packet. We don't know what format the packet is. We don't need to know. So if they decide to change the network layer with a completely different network layer, as long as it gives us some data somewhere in memory, say send this, that's all we want to know. That's one reason for layering the communication. You don't need to know how the layer above you or below you operate. And so the data link layer receives data from above or bits from the physical layer to be passed to either side. And this may involve link setup and disconnecting link with the nearest nodes. So you might have to do a link with the nearest machine. So you can't just send data to your neighbor. First thing, your neighbor has to be switched on. Second, it needs to have a transmitter that can communicate with our physical layer, transmitter and receiver. And once the physical layer is happy, they'll tell us they are okay. And then that's now when the data link layer starts working. Data link layer can only work if the physical layer is okay. If the physical layer tells you, I have no connection with my neighbor, then there's no point. You can't even communicate. So once the physical layer is okay, the first thing we need to get in touch with this neighbor of ours. Just same as, for example, you move into a new place and you find a neighbor, and the neighbor, first thing, they want to make a link with you. So first thing, do you speak the same language, for example? So that's going to start. That's what the data link layer on one machine wants to do, establish some form of agreement, some communication with the neighbor. Are you speaking this language? Are you using this protocol? Are you using this frame? What frame? What's the frame size? How big the frame is? All these parameters need to be negotiated. And once they're negotiated, they can start exchanging data. And usually the data comes from the network layer, pass it on to their network layer. But we need a layer to control the movement of data from one node to the next, or to the adjacent or the neighboring node, in the correct form and the correct rate. Rate, that means speed difference, and that's where flow control comes in. Specific functions of the data link layer: it provides services to the network layer. It determines how bits are grouped into frames, so it forms framing. It's one of its job is to build frames, and the receiver identifies those frames. Detection and correction of errors. That's also a function. In some networks, not all networks require that between two neighbors. And regulating the flow of frames. So if one neighbor is faster than the other, how do we control this so the faster sender cannot overwhelm the slower receiver? Just with the connection error detection between node to node. Before, which one is better? To do error detection at every neighbor, or just do it once at every end? Like when you send a message from here to Australia, is it better to only do the check once on this message in Australia by the receiving machine? And if there's something wrong with it, we keep sending it back, like the packet. Or is it better to send it to the next router? The router does a check on it. Send it to the next router, the router does an error check. And this is called link to link. So which one is better? Link to link or end to end? They call them link to link error detection or end to end error detection. Link to link. That's a good answer. Yeah, unless you need to verify, guys, from now on. You tell me it's this for this reason. Which one is better? Yeah. Anybody has any reason why maybe link to link is better than end to end? Or what's wrong with doing a check at every point? An error check, and remember, the error, whether you're doing it here, it's the same error check that you do it once at the very end. Do you do it 10 times, or do you do it once at the last machine? If you do it once at the last machine, if you do it at every point, then you're slowing down the communication. You're reducing the speed. Correct. So in your side, in your idea, then, in your mind, it's better to have end-to-end, because point-to-point or link-to-link error detection will take a lot of processing that will slow down the communication. That's correct. Any other advantage or disadvantage?
There is an error in the router.
Yes.
If we check end to end, then we never know where is the error.
Okay, we don't need to know where the error is. Can we fix it or not? Even if you do point to point, and the next router found where there's an error in what you sent me, the error can be due to something in the air, magnetic wave or noise. And the router tells you, hey, there is an error. So, which one is better? Come on, guys. Think of it.
It depends whether the error checking, the time for error checking offsets the time for sending the packet.
It would if you have to do. Remember, you're not just sending one packet. In some routers, you're sending as much or as many as 1 million packets a second. So if every packet at every router you're going to perform an error check in it, you're going to be performing millions of checks every second, which might delay those millions. Instead of going in 1 second, it might take them 2 seconds, maybe. But there is a delay involved. And then you're doing it at every router. So even if the error check is not very long, but the fact that you're doing it a lot at every router and to every packet, it will, no doubt, slow things down a bit. So that's almost, that's true. It's a fact that if you do error checking at every point, it's going to slow down their communication. Okay, but does it not have an advantage? Does the other one not have an advantage? What advantage does point-to-point have?
Probability of error occurrence is too much, then point-to-point will be better.
If the what? Error?
Probability of error occurrence.
Okay, yeah. If error probability, like how many errors are we getting per million? They check them. There's a rate of error. Especially in the old days, our equipment were not too good, or error detection wasn't as good, and even transmission and reception was not great. So we used to get a lot of errors, but nowadays there are very few errors. So it's probably, from that perspective, if you have less errors, what do you mean? When you go for point-to-point or end-to-end? End-to-end is better, yeah. So if the error rate is low, which most likely nowadays the transmission equipment is much better, then end-to-end is better. Any other points? What about if you discover an error? If an error happens that I transmit a frame to the first router, an error takes place, and that router transits it to the next one. And the other router sends it to the next one. I'm doing end-to-end now. So there's no checks, but there is an error developed at the first transmission, or to the first neighbor. So it goes all the way to Australia. The last machine discovers it and says, hey, there's an error there. So it has to send back all the way to me. Back here, there's an error in this frame. Can you resend it? And then I have to resend it. While if we were doing point-to-point, if I send an error to the first machine and there's an error in it, it tells me, hey, there's an error in this one, resend it. So I resend it, second time went okay, and then goes okay from there on. So the cost of correcting error, if you are doing point-to-point, the cost is very small if there is an error. If you're doing end-to-end, and you start sending a packet and it develops error at the early stages with the first or second or third router, and it keeps going all the way to the end, and then only to discover, because nobody's doing any checks in between, and then at the very end, the final router or the final device finds, oh, there's an error on this one, send back negative acknowledgement, maybe, ask the sender to resend it, so the acknowledgement comes all the way to here. It takes a long time again, and then me sending that packet. So by the time they get the packet, so point-to-point seems to be quicker at solving errors, at recovering errors, at correcting errors, rather than end-to-end. If an error happens. So if you have a lot of errors, this brings us to the point again, what's the rate of errors? Are we likely to get a lot of errors? Well, then you're better off going for point-to-point, because any error that happens, you fix it immediately. But if the errors are very rare, which nowadays, most likely errors are rarer, so there are very few errors, so we might get an error an hour. That's one error frame in billions of packets or frames. Well then, yeah, if the odd time that we send and there's an error, it's okay. We get a cost. Instead of having to do a check at every point for every frame, it's okay. We can put up with once-off every now and again that an error happens, it is still cheaper. So it depends on the error rate as well. But you need to know that the cost of recovery from error at point to point is much shorter than end to end. And from that perspective, you prefer point to point. But because the cost then of checking all frames all the time at point to point, that's very high, then from that perspective, we prefer the end to end. So the point is that there are few arguments for advantages of doing point to point error detection, because they say always that the quicker you discover an error in a system before the error gets too deep into the system, is the easier it can be cleared. Not just in communication, in most systems, but let's just stick to communication. So, and this is the main part that really brings the argument towards one of them. When you send information, is there a networks diagram here? No, there is not. Just for 1 sec, I want to go into this. All right. These are the routers, guys. Just a quick example of what happens when data is transmitted. Remember, the physical layer is at the bottom, data link layer, layer 1, 2, and 3, and the network layer is the top. So normally, every packet that's transferred normally will go from the network layer, the user at one machine, and it's going to the user at this machine. So the packet is formed here, it's passed to the data link layer where it's put into a frame, and it's transmitted there at the physical layer. And it's moved onto here, and that's where the error checking takes place. If we're doing point-to-point error checks, they're done at the data link layer, so it happens here. That's where we start reading the error. And then once we check the frame is okay, we pass it, we take the packet out, pass it to the network layer that decides, okay, don't send it to that router, don't send it to this router, send it to this one. So it sends it back to the data link layer, and the data link layer will start transmitting. We'll do a CRC check now from this point and up to this point. So the check is done here, CRC, for example, is done here, and CRC is done here, or error, any error detection at the data link layer. So it's done at this level, transmitted, gets to this point. So any error happens along there, it will be discovered. And then we take the packet out, pass it onto the network layer that decides where's the next router, and then the data link layer will also do an error check at this point and that point. That's CRC at this point. As you can see here, any error that takes place between this point, the CRC, the data link layer, to the next data link layer, it will be discovered. But we take that packet out of here, send it upwards. Now the packet is in this part of the router, and then the decision is made where to send it, to which the next router is given back to the data link layer, that we start error checking from this point to that point. But this part here, if an error happens, it's unlikely, but if an error happens here, it will not be discovered. Because the error check starts at this point, just before it's sending, and just immediately after it's receiving. But it's not looking for any error. For example, this frame contains 111, right? It's sent. It's received here 111. Okay, stop talking for a second. And then here at the router, it changed to 1101. When we give it to the data link layer and ask it to send it, it will take this as a packet, 1101, and sends it. So this guy sends 1101, and this guy receives 1101. They say there's no error. Pass it to our router. But see, the error happened up at the third layer of the router. Now, if this information was sent from the first machine all the way, no error checking, to the last machine, and it happens to change here at 1101, the last machine will discover it, say, hey, you were supposed to be sending me 1111, but CFC shows that I'm getting 1101, and that's an error. But if the error happens there and we are doing point to point, then it would not be discovered. So the problem with point-to-point error detection, it will not discover an error that happens inside the device, inside the router itself. It will only, error detection only happens from the moment you transmit to the moment you receive. What after you receive, you can mess it up, and nobody will know until you're going to start transmitting. Yeah.
But how can an error happen inside a router faster data?
Okay. Start trying to write the code for a router and see how many errors you develop before eventually it's perfected. Every program is tested for errors, and people tell you, okay, good, it's error-free. But did they really test everything in it? I'm not saying, routers are extensively tested. But if an error happens, it happens, so I'm not saying an error is going to happen, but this is what theoretically the textbooks are talking about. They say, hey, if an error happens there, it will not be discovered by your transmitter and the receiver of the next machine. It's from this transmitter, if you're doing point to point, from this transmitter to this receiver. With all what's gone, doesn't matter. It's your testing between this sender and that receiver. But if you're doing point to point, you're only testing from transmitter to this receiver. And from this transmitter to this receiver. What happens here is not tested. It's unlikely to have an error, but it's possible.
Theoretically, couldn't the same thing happen at the end router after it passes the data?
But the last device here will tell you there's no error. It will discover this error. It will discover this error. Yeah, maybe it's 1 in 10 possibility it might happen here as well, if it can happen in any of those. But there, for example, it goes through 10 routers. Any one of them could have an error. It's unlikely that it will happen, but it's correct. The idea is correct. The chances are slim. Yeah. Say again? Same question. Okay. Same answer. Okay. And it's for this reason and for the improvement in technology, in transmission and reception equipment, that it's probably now most likely it's in the favor of let's just have end-to-end. We know if an error happened, it costs us a little bit more to fix than if we were doing it at point-to-point. But to do point-to-point at very rare errors, and we are transmitting a lot more frames, at every second through every router to do all these millions and billions of checks, we get a lot more delays than if there was an error, end to end. So that's just a quick thing. So if you're asked which one is better, just, you need to give reasons. Don't say this system is better, this system is better. Say this system has the following advantages and the following disadvantages. This system has the following advantages, disadvantages. So, and then you can make up your mind. But this last reason, where errors that happen at intermediate nodes cannot be discovered by point to point, then makes the whole thing, it's better off to have end to end. It's cheaper, faster, and it can discover all errors that can happen in the devices as well in between. Okay, so let's get back to our All right, so we need a layer to control the movement of data from one node to an adjacent node and correct for errors and correct for speed. And therefore, we talked about framing. Oh. Framing is since the physical layer merely accepts and transmits a stream of bits without any regard to any meaningful of structure, it's up to the data link layer to create and recognize frames. So the physical layer doesn't recognize any structure, it's just ones and zeros. And barely, with the maybe scrambling techniques and all that. But really, the physical layer's main job is just to deliver data bits to you. And there's never a guarantee that they're error-free. So it's up to the data link layer to discover those errors. This can be accomplished by attaching special bit patterns to the beginning and end of a frame. So it takes the data, puts it in a frame, puts a header on it and a trailer on it. Each frame is a packet of data with a sequence number that is used to ensure delivery and a checksum or a CRC to track any corrupted frames. And there are 4 methods to recognizing frames. One of them is the character count. If we say all frames are equal in size, then, for example, 100 bytes, and that's it. Every 100 bytes, that's the end of a frame. So we don't have to, worry too much. But in our communication network, frames are not of equal size. They have a maximum size in most data networks, but they're variable size. Like you're downloading a file, like a file can have 1 million bytes. So you're sending 4,000 bytes each frame, for example, or each packet. And at the very end, you might be left with 100 bytes. You can still send a frame of 100 bytes. You don't have to send, not all frames have equal size. Most networks don't necessitate that, but it's one way to check, to identify frames. Maybe if we had the equal size frames. And if you're told that the header, this frame is 50 bytes, then you can read only 50 bytes. You don't need identifiers. And then character stuffing, byte stuffing, and bit stuffing and bit stripping, and the physical layer coding violations. Okay, character count is one simple but insufficient approach would be to begin each message with a field to indicate how many bytes. So you can send every message and it starts with the number 50. This is just like variable files. If you've done any databases or files, filing systems and computing, most our databases have equal size records. But not all of them. There are few of them that have variable size records. They use the storage better. Instead of every record has 500 bytes, but then, for example, we write the username. Some usernames take 80 bytes, some usernames take 20 bytes, but we have to have a username, maybe 100 bytes to accommodate everybody. But most of it is wasted storage space. So on some records, they have variable size records. Well, how do they know how big the record is every time you want to read the next record? Well, with the variable size record, they stick the size number at the start of the record. So I tell you, the following username you're going to read is 20 bytes, short name. The following username you're going to read 76 bytes, then you read them. So that's how you might identify the frames as well. Frames can be identified by having a number that indicates the size of the frame. Unfortunately, if any of the bits in the message length field gets damaged, then the receiver will have no way of getting back into the synchronization. Sometimes you lose data. That's okay. You lose a frame. Even the header can be disrupted. But hopefully that frame is gone, but hopefully you'll find the next frame that's what we expect a system that even if something goes wrong and you lose a frame, if we just depend on this number to tell you how big the next byte is, then you find lots of numbers after that, and you never get back into the start of a frame again. So just having a number to indicate the start of a frame and how many bytes are on the frame is not enough. Here's an example of how the character count was used to indicate the length of the messages or the frames to be sent. Every number that tells you how many bytes belong to that frame. But if you lose, if you miss that number, and if that number got corrupted, and you find another number somewhere else, you might think, oh, that's the new number now. And it's not good for recovery when an error happens. So start and end characters, that was used a long time ago. I mentioned it earlier on. So we have special character that's not normally used in the messages. Actually, they had two special characters, one to indicate the start of a frame and one to indicate the end of a frame. And it became, the problem is, what if now in my data I want to send a character that looks like this special character? And then they said, put two of them and we'll delete one, and we know if we find two consecutive ones, we know it's not a message. So we know it's a special character. What if I want to send 4 special characters in my frame? Then you have to send 4 others. So it wasn't really a sufficient good solution. So they started then going for the frame that has, they went for the idea of a flag, and then the rest of it, the header, the information, the trailer, and a flag again. So a flag that indicates the start and the end of a frame. And then with the flag, you need the bit stuffing and bit stripping ideas. These give examples, and here's a frame flag. Frame flag sequence is a fixed sequence in the protocol, 0, 6 ones and a 0. The flag may appear once between 2 frames. So you can have 2 flags. One indicates the end of this frame, and another one indicates the start of a new frame. But one flag is enough, they agreed. Even if you find one flag, it will indicate the end of the previous frame and the start for the next frame. The flag may, and the problem, frame flag problems, the problem is that the same sequence may be contained in the user data. We've already took examples of that. And to solve the problem, they use bit stuffing and bit stripping. The bit stuffing is inserting a 0 after every 5 consecutive ones. You look for the data, you keep searching the data. If you find repeated ones or consecutive ones, if you find 5 of them, you insert a 0. You start counting again. Find another 5 consecutive ones, put in a 0. And when the receiver checks that, every time it finds 5 consecutive ones, the receiver, it will remove the 0 in front of them. And that makes sure that in the user data or inside the frame, there's nothing that looks like a flag. And here's user data, an example of user data. You might be given an example like this. Say, okay, can you perform the bit stuffing on this frame before sending it? That means to hide the frame sequence. So you just keep looking for 5 consecutive ones. There it is, that's only 2. 1, 2, 3, 4, 5. We need to put a 0 here. And then 1, 2, 3, 4, 5, another 0 here. 1, 2, 3, 4, 5, another 0. And hold on. Yeah, and then the last few bits at the end. And the receiver needs to be able to remove those zeros. It just counts 5 consecutive ones and removes the 0. Error control, we've already talked about error control. We looked at 5 protocols for error detection, did we? CRC, did we do checksum? Yeah. And which one is better, CRC or checksum? Any idea? You don't, it's okay, you don't have to go back. I'll tell you the answer. Which one is better, parity error detection or CRC? What do you think? Okay. What's wrong with CRC with the parity error detection system? What's wrong with the parity error detection system? It will not detect what? It will not detect what kind of errors cannot be detected by the parity system. Even numbers of bits in the message. In the same byte, yeah. Thank you. CRC would discover. What errors CRC cannot discover? Anybody remember? It will, okay, well, maybe you should tell me all the errors that it will definitely discover. Or what discovers it will what errors it will definitely discover 100%? CRC, what errors it can discover? Okay, I'll make it easier for you. It's gonna be, it will discover 100%, either all errors that are even number of errors in the message, or odd errors in a message. Which one of those is discovered 100%? What did you say? Or even. Oh, even. Even or odd? I can't hear you. What do you think? Which errors will be discovered? The even errors or the odd error? CRC will discover 100% in a frame all errors if the number of bits that involved are even or bit or odd. Anybody remembers? Whew. Okay, we should have done some more tutorials. Okay, odd. Okay, I'll make it easier for you. It's odd. CRC will 100% discover all odd errors in a frame. You know, it doesn't tell you where the error is, yeah, but it will tell you there's an error. What about even errors? Will it discover even an error of 6 bits or 20 bits or 12 if the number of bits that change in the message are even? Somebody say yeah. Answer, don't say yeah. Okay. We'll use that. We'll have another revision of that sometime. Okay, but all errors, it will discover all errors, 100% of the errors, if they are even errors, but if they are shorter than the generator. If they are shorter than the generator, they be discovered, whether they're even or odd. But if they are longer than the generator and they are not odd, if they are even and longer than the generator, they'd be discovered at the rate of 99.9%. Okay. And then we talked about flow control as well as the responsibility of the data link layer. And we talked about the acknowledgement and the negative acknowledgement. Which one is better, an acknowledgement or a negative acknowledgement? What's the difference between an acknowledgement and a negative acknowledgement? Any idea? Okay. A negative acknowledgement is used in the system. It just normally indicates an error or something wrong with one frame, and it requests the retransmission of one frame only. The acknowledgement can indicate something wrong with one frame, but it'll ask you to retransmit. Go back to this number and keep transmitting all your frames from that number onward. The acknowledgement can be negative acknowledgement as well. Like if he send me frames 1, 2, 3, and 4, and I send you acknowledgement 1, that's really a negative acknowledgement. I'm telling you, I did not get number 1, or 2, or 3, or 4. So, but as used in the system, in the error detection system, NAC is specifically talking about one frame, and the Ack normally talks about a group frame starting from a particular one. Okay, so that's the NAC and Ack. How does the timer work? Oh, I don't know. What's the retransmission timer? Any idea? How long is the retransmission timer? Anybody can give me any idea how long it is?
It waits for the acknowledgement from the receiver. If the receiver does not send an acknowledgement, it will wait for a while and then again send the same frame that it sent earlier, or the previous frame.
Okay. So that's the idea of the retransmission timer is if information in frames are sent and no acknowledgement is received, after a certain length of time, the timers will allow the system or make the system resend those frames again. That's the main idea of the retransmission timer. Normally in this flow control system we looked at, when a sender sends a frame or a group of frames, it goes asleep and waiting on either of two events. What are these two events? Any idea? When you send 5 frames and you go to sleep, what will wake you up? Before the timer?
Or the
The acknowledgement. So you're waiting to receive an acknowledgement for the frames you sent. So an acknowledgement will come back, or the timer. If an acknowledgement never comes back, for some reason, maybe the acknowledgement is lost, maybe the frames you sent are lost. Then the timer, retransmission timer will go off, and that's like an alarm you set before you go to sleep. But my next question was, how long is the timer? You are the administrator in a network, and you are asked, how long will we make the timer go for? What would you say? Anybody? Anybody wants to have any suggestions? You don't necessarily need to come up with a number. Anytime somebody asks you how long, it doesn't always mean 40 milliseconds. It can be, yeah? Yeah. It depends on how fast, when you send a frame, how long does it take to send the frame to your neighbor? How long does your neighbor take to process it? And how long does it take to send it back? And we get this total time, multiply it into 10 or 20, and that will be your retransmission timer. So you don't make it a very short retransmission timer, that will be going up all the time. Yeah.
Does that mean the first session doesn't have timer? Because it's like
The network can have a timer. At the network, they tell you, retransmission timer is 30 milliseconds. Then you have to stick to that.
But we get to know after seeing the response.
Pardon?
Because you say the timer goes based on the time the receiver gets a response. So does that mean the first
Maybe the network administrator will reset it every now and then. An automatic application that every minute or two send a few test packets, receive them, calculate and notify everybody. Maybe that's, but it's possible. It can be a network defined value. I had another question, I forgot it. Okay, error detection. So we went through error detection. All right. We did Hamming code. What's the advantage of Hamming code? Advantages of Hamming code over CLC. Fix zeros as well. What's the advantage of having code over CRC? Yeah?
It shows exact index of error.
It can tell you which bit has the error. So if you knew where the bit with the error, you can fix it at the receiver end. You don't have to retransmit the full frame. But what's the disadvantage of having code? Disadvantage of having code. Anybody has any disadvantage of having code? Pardon? It's efficient at finding one bit error. If it's any more than that, it's not efficient for finding multiple bit errors. Let me make sure the attendance is on. Just x to the power of 4 plus 1. That's polynomial generator. Convert that into binary. X to the power of 4 plus 1. You convert that into a CLC generator. 10001. Yeah. Okay. Let me check the attendance, please, and then.